So welcome, thanks for coming. This is our week 5 webinar. So let me share my desktop and we can talk about the plan today and the topics. This is a pretty big topic actually. So let me go ahead and share my screen. Okay, you should be able to see my screen now, and the plan is I'll start out with any questions you might have, and then we're going to get into sampling distributions. So today's a bit of an abstract day, but it's a really important one. Everything we do pretty much from now on uses this. So pay attention. There's a lot of details. It turns out it's not usually the one that everyone has trouble with, though. That's the good news, but it is really important. I'll get into biased versus unbiased estimators, talk a little about that. Then we'll get into the central limit theorem for means. So the central limit theorem, and there's 3 parts of it, is the most important theorem of all of statistics. So it is the theorem. So today is the big day, and everything we do from now on is going to use it. So we'll get into this, and I'll talk about what the central limit theorem is for means. Then I'll get into the central limit theorem for proportions. So remember, means, you can get a mean if you have a quantitative survey question, and then you can take a mean as just the average. Whereas the central limit theorem for proportions, that is a survey question that might be a yes or no question. And then you can find out what are the proportion of people that said yes. So we'll talk about the central limit theorem for proportions. And then finally, and we'll briefly do this piece, and that is the central limit theorem for sums. So that's if you want to find out, instead of what's the average of something, but what's the total. And that's actually not that big a deal. But the first, number 4 and 5 here are really, really important. So that is the plan today. I want to remind you all about something important. What is due at the end of the week?
Projects.
Yeah, project 1 is due at the end of the week. So at this point, you should be either done with your first draft, or you should be very close to done with your first draft, because you need to get the project to me as a draft by hopefully Wednesday night, or even by today. If it's not emailed to me by 8 in the morning on Thursday, then I don't read it. That's my rule. Okay, and I only read one draft, by the way, but I'll give you lots of feedback, and then I'll be happy to answer questions about the feedback, but I only read the whole draft once. Otherwise, you know, if I read each draft 100 times, then it would be thousands of pages of reading, and I don't have that time. So, but I really do want to read your drafts, and I want you to do well. And I want to remind you that Braulio is also here to help, and he'll look at your draft too. So I'll read it once, he'll look at it once or as many times as he wants, and we'll all answer questions for you and help you out, and make sure that you know, you're in it together as a group. So as a group project, so make sure that you're looking at the whole project, not just the piece that you wrote. Make sure you look at what your partners wrote, and you can talk it over and see what needs to be fixed and that kind of stuff before and after I look at it. So that's the big thing coming this week, is the project. Okay, and we do have the central limit theorem for the chapter 7 material to do too. So that is the plan. Are there any questions about anything? Any questions? Okay, if there are no questions, then what I can do is talk about new stuff. And I have a question for you, and my rule is you have to answer it. But if you don't feel comfortable, you're welcome to just make up some number that's reasonable. That's my rule of any kind of question that I ask. And also, it's going to be in the chat box, which is not recorded, so no one will see your name on the answer. So the question is, how many hours a week do you work? So I want you to put in the chat box, how many hours a week do you work?
In this class or for a job?
For a job. You know, work means getting paid. Yep. And the hope is everyone answers. It should be, yeah. 35. Okay, oops, 35. Okay, so we just got a bunch of numbers. I'll make them a little bigger so that we can see them. And here's the thing. In the real world, you know, you're interested in the entire population, and that might be all students, for example. You're never going to be able to get that. And that's why you take samples. Okay, and we're going to do a little you know, fun thing where we're going to call you guys the population, and we're going to take samples. So we can actually go and find the mean and standard deviation. It's not that hard with 5 numbers. The good news is we can do it the really easy way and just go to the calculator. And that is number 8. No, this is number 8. It's not grouped. That'd be if it was like there were 7 of you and you took the average of 7 and 7 different ones, and that, or how many said this, how many said this. So you can do it a little easier. You could do standard deviation calculator. I had a better one. Just a minute. I thought it was in here. Frequency, relative frequency, box plot, online calculator, mean and median, online calculator, standard deviation, mean and standard deviation group frequency, z-score, expected value. Table. Oh, I know why. I need to go to 46. I knew there was something wrong. I apologize for that. I wasn't on the calculator. I was on a link that goes to the calculator. That's better. And now we can go to number 3. This one we want. Sorry, number 2. Sorry about that. And then we can put in your answers. And again, I'm considering you all the population. So I'm going to make it a population and calculate. And the mean is 22. And the standard deviation is about 18. Okay, and we've gone over this already, so hopefully you all understand what mean and standard deviation are. If you don't, the project won't go well, by the way, because those are big parts of it. So now I'm going to have you do the following. I want you to randomly choose 3 of these data values. Okay, and I want to remind you, for random, you don't know how to do that in your head. And by the way, not because you know don't have a degree in statistics. People don't. It's a psychology thing. But you can always ask a computer to pick 3 numbers from 1 to 5. And if it picks, say, 1, 3, and 4, you do 40, 0, and 0. So let's see if you can pick 3 random numbers from 1 to 5. And then grab those numbers. Give you a minute to do that. And I want you all to do it. It's important that you all do it. So pick 3 numbers. You can even ask your phone to get 3 numbers from 1 to 5. Okay, so there's a lot of ways. I also have a random number generator too. That works too. But there's a lot of ways of getting random numbers. So get 3 random numbers from 1 to 5, and then write them down. Give you a moment. And what we're doing is we're doing kind of an example of what surveys are all about. Okay, I don't need you to put in the 3 random numbers that you picked. I want you to put in the mean and the standard deviation, and that's the sample standard deviation for your 3 numbers, because that's what we're interested in. Okay, so I'm going to let you find the mean and standard deviation for your 3 numbers and put the mean and standard deviation into the chat box. The mean you probably can do in your head, add them up and divide by 3. Okay, and remember you're picking, so if you got, 3, 2, and 1, for example, that'd be 0, 35, and 40 would be your numbers, by the way. So let's see if you can do that. Shouldn't take too long. But it's important to go through this exercise so we can kind of understand what sampling distributions are all about. When you have the mean and standard deviation, put it in your the box. Okay, we got a mean. And again, if you use that calculator I was showing you, then it'll give you both. Because mean you can do it ahead, but standard deviation is much harder. Okay, so there we go. We got one, which is 25 and 17.8. And hopefully all you have one too. I don't want to spend all day, but 25 and 17.8. Okay. We have another that was 25 and 21.9. Okay. So what I want to emphasize is a few things. One is that the mean for the population, we use the letter mu. The mean for the sample, we use the letter X bar. Got it? Any questions on that? Just like the standard deviation for the population, we use sigma, and the standard deviation of the sample, you use S. Okay, and in the real world, you don't know mu and you don't know sigma. And what you tend to try and do is you use your X bar to approximate mu. That's kind of the goal. Okay, and the X bar comes from the sample, because in the real world, you usually can only take a sample. Okay, this example, we could do all 5, but in the real world, it might be all Americans, for example. Okay, so you take a sample, and here our sample size was 3, okay, which is a very small sample, but I wanted to make sure that we knew we could do it. So it's very important that you understand the letters that we use. And we've talked about these letters already, but we're going to have new ones today. So we're going to have a bunch of sample means. I'm going to write a couple. There was a, let's see what we got here. We got 25, 25, 6.3. And then, let's see, 25, 25, 6.3, and there's others. I'll just put ... So there's sample means. Again, in the real world, you might be doing a sample of, I don't know, how many hours a week do you work? And you were looking at, students in California, and you might have a sample of size 100. And then if you looked at all the possible samples that you could get, there's literally billions and billions and billions of samples of size 100 out of students. You can't list all of the sample means in the real world. Okay, with this example, we could, there's actually 20 of them, but you can't list them all in the real world. But what we can do is we can say, when you have a population, and if you're going to take samples of the same size, and let's say that's your career, your job in the world is to do studies, then you can look at all the different samples that you could possibly take and look at the means of those samples. And if you have a lot of numbers, then you can look at that as data. And then you could do things like, what is a histogram for those numbers? Or how about what is the mean of those sample means? Does that make sense? What is the standard deviation of those sample means? And when I say those, I mean all possible sample means and all possible. So the standard deviation of all possible sample means and the population mean of all sample means. This is where it gets a little confusing, because we're looking at what's called a sampling distribution, which is a distribution of all sample means.
So just so I'm following this right now, 40, 35, 0, 0, and 35 are a sample of a population. And then we took 3 other samples of the sample. Kind of.
Actually, what I looked at is this is the population, just to
Oh,
make it,
okay.
just
So
for this example.
this is the whole population.
That's the whole population. And for the population, we have a whole bunch of sample means.
Oh,
Do you see that?
yeah, I do see that. So
I mean, in our group, we only got 4, but we could get, there's 20, it turns out there's 20 different ones. You can trust me on that. That have to do with binomial distributions, or combinations, just believe me on that one. But there's a lot. And in the real world, you're going to have a very big population with much harder bigger sample sizes, and you're going to have millions and millions of sample means.
Was 3 just an arbitrary 3
Yeah.
data values? Just
Yeah, in the real world, you don't use 3. It's too small.
Yeah, for sure.
But I didn't want you to spend all day on this.
I get it. Okay.
Yeah. Yeah.
And then you take the mean of the sample.
Exactly. The mean of all possible sample means. Okay, and that's where this gets confusing, because now we have 3 different kinds of means. We have the population mean, we have the sample mean, and we have the mean of the sampling distribution.
Nice.
And the mean of the sampling distribution is the mean of all possible sample means. So I apologize if it's confusing.
No, I get it.
It's really important. It's what we're going to do for the rest of the entire course. Okay.
Yeah, it all builds on itself.
Yeah, and we're also going to do the population mean of all possible sample proportions when we talk about proportions. So that's going to go also. Okay. So the letter we use, the symbol we use for the population mean of all possible sample means, because it's a population mean, that's mu, of sample means, that's x bar. So they use mu subscript x bar. And that is the symbol that we use for the population mean of all possible sample means. Any questions on that? Okay, I know that's a little confusing, but hopefully you'll do this for a while and you'll get used to it.
Does this give us like a more accurate mean, or why do people do this?
Okay, so here's the reason why you do it. Okay, you do it because what we want what's called the central limit theorem.
Okay.
So I'm going to let you know, be a little patient, not too patient because we're almost there.
Okay.
Okay. And by the way, I'm going to be using this for something that could make you thousands of dollars. Literally, by the way.
Nice.
Okay. And by the way, for me, hundreds of thousands. Because, like, and it's not my teaching job. Okay. And I'll explain it. And most people don't know statistics well enough to be smart enough and to do it. And hopefully you'll learn and you'll make some money when you get older, when you learn how to invest.
I hope so.
Okay. So then we can also talk about the population mean of the sampling distributions. And we can talk about the population standard deviation of all possible sample means. Well, since it's population standard deviation, that's a sigma. Of the sample means, that's an x bar. So we use sigma subscript x bar. And that is the populations, that's the standard deviation of all possible sample means. Also called the sampling distribution. Okay, is what we're looking at. Okay, this sigma sub x bar is also called the standard error. And you'll hear that a lot. That's a biggie in statistics. We're going to be using this for the whole class, basically. And I will let you know, I don't want to confuse you too much, but project 1, what did I tell you had to have a paragraph on?
Standard deviation.
Project 2, you're going to have a paragraph on standard error. Okay, now, right now, all I've done is defined it. We haven't used it or talked about it much. But you're going to have a whole paragraph on standard error for project 2, so don't worry about it yet.
Is each project worth 20%, or both projects?
Each one's worth 10%.
Oh, okay.
Yeah, so it's 10% for project 1, 10% for project 2. Okay, which is a big deal. If you don't do it, you lose. You can't get any in the class, basically.
Yeah.
Even if you get 100% on everything else, minus maybe 1 point, you can't get any in the class if you don't do the project. Okay, so they're important. Take them seriously. Okay, but they're not your whole grade. All the other stuff is important too. Okay, any questions on the standard error? Okay, so then this definition, and this is what I was just talking about, is a sampling distribution. Let me make it bigger. So the sampling distribution for a statistic of samples of size n. So in our example, we use samples of size 3. Okay, and by the way, 3 is not a big enough sample size for anything you do in the real world. I want to give you a warning. In fact, at this point, you might have a guess of how big a sample size you need to have anything useful.
100?
100 is a good guess, but that doesn't come from anything we've talked about in class. It's something that we've talked about.
30?
What did you say?
30? Because that's what the project requires?
Really close, except 30 wasn't
Oh,
enough
30.
for the project.
31. Sorry.
31. So more than 30. So 31 is like the minimals for, and this is the standard statistics books, is that if you have under 30, you don't have very good data. So you want to have a pretty big sample size to be able to have good data. And we'll talk about what that all means in a bit.
Really? 31's enough? Like for
31's enough for about 1 decimal point of accuracy.
really?
Okay, one significant digit, one extra significant digit, or maybe 2 significant digits of accuracy is typically for a mean.
Oh,
Yeah. For a mean. Population proportion is actually much more complicated.
Yeah.
But for means, and for project 1 was about means. Okay. So now comes another definition. Okay, a lot of definitions, and then we'll do examples, I promise, and not just our little example. But we got our big theorem in a minute. And that is a statistic is an unbiased estimator for a parameter. Do you remember the difference between a statistic and a parameter? Very important.
One is for population and one is for sample.
Right, but let's say it the other way around, since statistics is read first. Statistic is read for the sample.
Parameters for the population.
And parameters for the population. You're right with one, but I want to say it in order, just to remind you. So a statistic is a number that you get from a sample, and that could be the sample mean. And a parameter is a number you get from the entire population. Okay, a statistic is an unbiased estimator for the parameter if the mean of the sampling distribution for that statistic is equal to that parameter. Okay, so let me give you examples. So the sample mean is an unbiased estimator for the population mean. So kind of the idea, if you take a sample, okay, and when I say sample, I mean with unbiased data. That's very important. So if you take a sample with unbiased data and you look at its sample mean, and then you do it again and again and again, that's your life. And you look at the mean of all the different possible sample means, that actually is the population mean. So that's a big deal. So the sample mean does work. The sample range is a biased estimator for the population range. So an example is if I took a sample of, let's say, 31 students, okay? And I surveyed them on how tall are you, got it? And I looked at their heights, and I found the range of those 31 students' heights. Is that a good guess on the range of the entire population of all students in California, for example? It isn't, because the range means the very shortest of all students in all of California. And then you look at the very tallest of all students in all of California and subtract those two. Okay. By the way, I did have the tallest student in 1 year. He was 7'7" of all California. I don't think I've ever had the shortest. But the chance of you getting the tallest and the shortest out of 31 randomly selected students is like almost none. Does that make sense? So if you used your sample range and thought that was a good estimate for the population range, you're wrong. It's just a bad estimate. Does that make sense? In particular, it's an unbiased estimate, and it's unbiased because that the population mean of all possible sample means, the population mean of all possible sample ranges is going to be smaller than the true range. Does that make sense? And same thing if you ask income of Americans, for example. If you ask 31 people what their income was, and you looked at the average of all ranges of 31 people, you're not going to get the range of all Americans, which happens to be, I don't know who's number one now. Is it Bezos or is it Musk? I'm not sure who's the richest today. All depends on what the stock market does, right? And then subtract 0 and that'll give you the range. But if you ask 31 people over and over and over again, you're not going to get that range, you know, except maybe 1 in a million times or so. Does that make sense? So the sample range is a biased estimator, which means you should not use your sample range and think, now I have an idea of what the population is. But you can use the sample mean and say, I have a good idea of the population mean. Does that make sense? Okay, it turns out the sample proportion is an unbiased estimator for the population proportion. So if you asked, 100 people, randomly, I don't know, maybe, are you pregnant? Because that's a good yes or no question, right? Then if you ask 31 people over and over and over again and took the proportion, took the average of all those proportions that you could ever ask, you'll get the proportion of all people who are pregnant. Does that make sense? There's no bias there. So it's a kind of your best guess. Okay. I'm not putting this in the list. What big statistic did I not write down? Hopefully you all know. What's the other really important statistics in this class?
Standard deviation?
Yeah, standard deviation. It turns out the sample standard deviation is a very slightly biased estimate for the population standard deviation. But you're usually good within a couple decimal places. And if you have a large sample size, it's good enough for anyone who cares, but it's never perfect. So I'm not putting it here because it's so close, but not quite there. Whereas the range is just way off. Does that make sense? Okay, now comes the central limit theorem. It is the most important theorem of all of this class. And it's the following. The sampling distribution for sample means, okay, for samples of size n has mu sub x bar equals mu, which is basically saying that the sample mean is an unbiased estimator for the population mean. Any questions on that so far? Okay, so I want to pause because it's so important. You need to know it. Okay, I would have it written down in front of you for the rest of the class for everything you do in class. That's how important this is. And B is even more important because A is kind of obvious. It's easy to remember that they're just equal. Okay, the sampling standard deviation, the standard deviation of the sampling distribution, of the standard error, is not equal to the population standard deviation. It's actually equal to the population standard deviation divided by the square root of the sample size. So I'm going to put this one bold and let you stare at it for a bit because it's that important. Okay, so sigma sub x bar equals sigma over the square root of n. All right, so let me tell you why it's so important. If you think about it, the standard deviation is kind of how much things fluctuate, right? So the idea is that we know that mu sub x bar equals mu. So if you take a sample mean, your sample mean probably is not going to be exactly the same as a population mean, right? If you just look at x bar, not mu sub x bar, you look at x bar, it's probably not going to be the same as the population mean. So if you looked at, I don't know, say an average of, 30, 35 people or how many people in your project, right? For your project you did, and you looked at your sample mean. The sample mean you got for your project is not, almost certainly not going to be exactly the same as the population mean, which is what you're most interested in, right? But you can never get the population mean because the population is too big. So the next question you would ask is, how good an estimate is my sample mean? Does that make sense? Well, if the standard deviation of all sample means is very, very small, then you have a good estimate. You're very likely to have a good estimate, because if the standard deviation is small, then you're very unlikely to be far from the true mean, which is the population mean. Do you remember that in our class that we've been doing? So you would like to have a very small sampling standard deviation or standard error. Does that make sense? And what this says is that if you have a large N, let's say you have an N of 100, then sigma over root N is 1/10 the size of the population standard deviation, which might be really small. And if that's really small, then you could be very comfortable that your sample mean is close to the population mean. And the bigger the N is, the more comfortable you are. And the word we use in statistics, which we'll do next week, is confident. So it's the more confident you are that your sample mean is close to the population mean. Any questions on this idea? It's a very important idea. Maybe the most important idea of the entire course. And it's a little complex, so that's why I'm saying it 5 times.
I think I get it, but I'm not sure if I have it. So can I explain
Sure.
it back to
Sure.
you?
Sure.
Okay. The first thing you said was that, like, in a normal sample, the closer that the standard deviation is to the mean.
It's to 0, not to the mean, but to 0.
Oh, to 0, yes. Then the more the data points are clustered around the mean.
Right.
So that the error is smaller.
Mm-hmm.
Okay, so I'm not sure how that relates to how the more samples you have in the square root of N,
Mm-hmm.
the smaller your standard
Error.
is going to be.
Right. And that's because if you divide by a big number, you get a small number. Does that make sense?
Oh, okay. Yeah.
Yeah. So if N is 100, you're dividing by 10. So if I started with, say, a standard deviation of 30, well, my standard error will only be 3 because I just divided by 10.
I got that. Okay.
So then that means that you're more likely to be within 3 of the population mean. Do you see? Whereas if you only grabbed one person, then you're likely to be within 30 of the mean, which is not nearly as good as being within 3. Do you see that?
Okay, I got it.
And the larger the sample size, the better. Okay, now comes the second piece of the central limit theorem, and this is very important. And that is if the population's distribution is normal, or if the sample size is large, and for our class, a definition of large is greater than 30. And subliminally, I threw greater than 30 at you for the last 3 weeks or so. Okay, then the sampling distribution for the mean is also approximately normal. So the idea is even if you have no idea what the distribution is, if you take a sample of size 31, then the sampling distribution is going to be approximately normal. Any questions on that? And what's wonderful about being approximately normal is then you could use the normal distribution calculator to find any probability. Whereas if you don't know the distribution, you can't find the probability. You have no chance. But if you know it's normal, then we have a calculator for it. I'm going to show you something. I think it's worth it. Now that I think of it, I created an app. As I think y'all know, I'm a programmer. So if we start out with a normal distribution, there's a good normal distribution, and we take a bunch of samples of, let's say, sample size 2. How about 9? Let's go sample size 9, just for fun. What this just did is this just grabbed a bunch of samples of sample size 9, took the mean of each of those samples, and then made a histogram of those means. Can you see the picture? And you'll notice that that histogram is approximately normal. You see that? But you'll also notice the standard deviation, right, is much smaller. There's less of a wide spread than what we started with. Do you see that? Not only is it smaller, we started with 67 and now we're at a little more than 22. Well, guess what? 67 times the square divided by the square root of 9 is about 22. So it made the spread smaller because of the central limit theorem. But I could go to a new distribution. Let's say you had a skewed left distribution. Okay, and if I only had a sample size 2, does that look like a normal distribution? Right, it doesn't, does it? Our sample size is too small. We need to be large. Instead, if I did 100, now it looks a lot more normal, doesn't it? Because our sample size now is bigger than 30. Okay.
How many times are you taking 100?
What's that?
How many times are you taking 100 samples?
Number of samples, 2,500.
So you're taking, okay. You're
So
taking
2,500 samples of 100, and then I make a histogram.
So 2,500 random samples of 100.
Right. And there's our histogram of that.
All right.
Okay. And by
how
the way,
many-
you never want to do this by hand. This is for computers only because it would take you for the rest of your life to do that, right?
Yeah.
Good luck. But computers are good at doing that.
How many, does it matter how many were in the population or no?
You mean whether this was 2,500 or 10,000 or something?
Yeah.
Not really. If it was 10,000, it'd be a little smoother, but it would take too long for the computer to do it.
All right.
Yeah. But n equals 36 matters. So notice it just got a little wider, didn't it? At n equals 36. But it's still approximately normal.
Why are you changing the number of samples though every time?
Oh, because the computer can handle more if there's a smaller n.
Oh, okay.
Yeah, that's my you know, I didn't have to tell you how many samples, but since you asked, it's there. And it had to do with time for the computer to handle it.
Yeah. Hey, one other
That's not
question.
statistics, that's computer programming. You don't have to worry about it.
One other question. So when you say 30, so like, or 31,
Mhm.
is that like if it's the population is the entire United States or the population is an entire college campus? I mean,
It turns out it makes no difference.
there's no ratio like that it gets
You
higher.
need to have at least 5 times, at least I think 20 times more to make it work really well.
Okay. So it could be
Usually that's not a problem because if you have 30, if you have 100, 20 times that is just 2,000, and populations are almost always bigger than that anyway. So
yeah,
it's not something you worry about. That's not elementary stats, so I'm not going to get into it. Sound good?
yeah, for sure.
I don't understand the theorem and how it relates to how it becomes normal when it's a higher sample of samples.
Okay, so that becomes normal. You just have to. So what that means is if you draw a histogram of all possible sample means, then that histogram will look pretty much normal shaped.
Always?
As long as the sample size is bigger than 30.
Okay, I got you.
Yep. So if I do this again, it changed a little bit, but it's still looking pretty normal. Do you see that? It always will be. And that's called a theorem, which means it's always true. That's the good news. We are assuming that it's an unbiased sample. With a biased sample, you can't ever say anything ever about anything. Does that make sense? So this is for unbiased sampling. So that's the good news, is it just always works. And the other good news is it's so hard to understand the proof that you don't have to ever know it. The only way you'll learn is if you decide to get a master's degree. Undergrad's not enough, a master's degree in mathematics or statistics, because it's brutal. So I learned it, but you definitely don't need to know that. You need to know the result. Okay, so normal is important because that means that we can actually calculate probabilities. Whereas if we had this skewed thing, good luck finding probabilities, who knows? Or we could do a new distribution. This is my favorite. I'm going to call it the Manhattan distribution. You know why I call it the Manhattan distribution?
It looks like a city.
Looks like a city. Okay, just some weird distribution. We don't have a name for it, so I'm just calling it Manhattan. Okay. And then if I let n equals 100, looks pretty normal. So any distribution, doesn't matter what you start with, if you have a large sample size, the sampling distribution is always approximately normal. Any questions on that? That's a huge, huge deal. Okay. And the over 30, by the way, this is for the means. I want to tell you a lot of times today, if you have proportions, 30 is not a number you ever want to use. Got it?
Why?
We'll get there. We're not there yet. We'll get to proportions. We have to get to proportions. I'll tell you what we're going to be using. Okay. So here's something that I have been using most of my life now. All right. So here's the thing. Let's suppose, and again, I have no idea what you all have in terms of your bank accounts, but let's suppose you had $10,000 and you decided to take your $10,000 and put it in the bank. Sound good? Okay. Now I went online actually a couple hours ago and I Googled the average amount of interest you get on a bank account, and it said 0.03%. Okay. So 0.03 is your mean interest rate. Does that make sense? The standard deviation, if you put it in a bank, okay, and like Bank of America or Bank of the West or Wells Fargo, one of those banks, the standard deviation is 0. How come?
Because there's no, it's just solid. There's no variation on it.
Exactly. And you may have heard this, you may not. Yeah, I'm sure you've all heard it, but you may not know what it means. Because all the banks I just talked about are FDIC insured. You know what that means?
You can't lose your money.
Exactly. Even if the bank goes out of business, then the government of America will give you a check and they'll give you the money. So you can't lose your money. I mean, I guess if, there was a world war and America fell down and there was no more America, but I'm not going there. Because I don't think there'll be people left if that happens. So let's hope not. Okay, so the standard deviation is 0. Is this a good investment?
It's okay.
Yeah, right. Up to 25,000, but we're only putting 10,000 in. So the FDIC insured actually works. Okay. All right. So it depends. If your goal is to make money, this investment sucks. You're putting 10,000 in. At the end of the year, you're getting 0.03%, by the way. So you're getting $3. Okay. That is not a lot of money made. But you have no risk. All right, so that is one choice for investing your 10,000. What are other ways of investing besides putting into a bank?
Stock market?
Yeah, stock market. So let's suppose that you invested in a stock, okay? And I'm going to make an assumption, which we need to use. By the way, I knew you'd say stock market. I even had it all typed out for you. because that's the place to put it. Okay, there's other places too, but that's one of the obvious places. So let's suppose you put your money, your $10,000, and you randomly selected a stock. Got it? You're going to randomly select a stock, which you can do with a random number generator. You can look at all stocks and pick a stock. Okay. Then the mean over the last many years, 20 years or so, is about 9%. That's a lot better, isn't it? But the standard deviation is 20%. Okay. With stock, you often lose money, but you often gain a lot of money. Does that make sense? You rarely get exactly 9%. Okay, so unlike the bank account, there's actually risk. The probability of losing money by putting it into the bank is 0. So assume that stock returns are normally distributed. They're not quite, but we're going to make the assumption for today. What's the probability you're going to end up losing money? And I want to let you know this is a question from last week, but you should know how to do it. So first thing, if you want to find the probability of losing money, that's the same thing, the probability that X is less than 0. Because if your interest that you get is negative, that means you lost money. Hopefully that makes sense to everyone. Whereas if your interest is 0 or positive, you didn't lose money. Sound clear? Okay, so we assumed it was normal. So X is approximately normally distributed. And the mean is 9%. And the standard deviation was 20%. Now we can quickly do this. This guy. And I can go to the normal probability. So our low is, it's actually 0, but I'm going to go negative 9999 because we're assuming it's normal. And our high is, sorry, low isn't actually 0. Our high is 0. Okay, the actual low is negative 100%, but I'm not even going to write that. The mean
It's 9.
Was 9. The standard deviation
20.
was 20. Okay, and I tried to make the calculator easy. Okay, and here we are. You have around a 33% chance of losing money. Okay, so let's suppose I'll give you my example that I always like to use, and I'll tell you, it was a long time ago, decades ago, and that was I wanted to make sure that I had money to pay for my daughter's education. Sound good? And I would just almost not live with myself if the money ended up losing money and I didn't have enough money to pay, and then I have to tell her, sorry, I suck at investing. So that doesn't work, okay? So do you think I was okay with a 33% chance of losing money in that kind of account?
No.
Yeah, so I wasn't okay with it. Okay, I was not okay with it. So this may not be a good investment. Okay, on the other hand, by the way, I have what I call my fun money. Okay, somewhat fun. I have funner money also, by the way, which we'll talk about also another day. I have my kind of fun money where if I lose money, it's not the end of the world. You know what I mean? If I lose 20% of money that I put in the market, I don't have to like tell my daughter she can't go to college. You know what I mean? So I call that money that is okay if I lose some money. Do you see the difference in terms of investment strategy? Then a single stock is actually pretty good because you're averaging 9%. Okay. And the standard deviation is 20%. So in fact, let's suppose I want to find out what's the probability of making 30%. I can do that very easily. Low would be 30. The high would now be at least 30%. So let's throw a bunch of 9s in. And I can calculate that. Whoops, I need to make probability blank. And there's almost a 15% chance I'm going to make 30% on my investment. It's pretty darn good. Any questions on that? So if you don't mind the risk, a single stock is pretty good. But there's another choice besides a single stock when it comes to stock investment. Anyone know what it is? You have to know a little about investing to know.
Like a mutual fund, like an S&P 500?
Exactly, a mutual fund. Okay, so the example I've got is the following. Instead of the S&P, sorry, I didn't put in the S&P, but I put in the Dow Jones Index Fund. Same idea though. So let's suppose instead you chose the Dow Jones Index Fund, which, by the way, what that means is that you put into a company, and that company takes your money along with many other people's money, by the way, and invests it in the Dow Jones, which is a collection of 30 stocks, almost over 30. So kind of good enough for normal, by the way. It's not quite there, but it's really close. Okay. And if you do S&P index fund, then it's definitely over 30. Okay. Then what's the probability of losing money?
Less.
Okay, well, let's find out. So we have to do a lot of things. We have to assume that the Dow Jones is representative. Okay, we have to assume the stocks are independent of each other, which they're not really, but for this class, we're gonna have to assume it. If anyone knows anything about investing, what's the word for making sure your stocks are independent of each other? There's a word for it. You all have heard the word, but you may not know it when I ask you. It's a business word, not a stock, not a statistics word. No? Okay, it's called a diversified investment. Y'all heard those words before? Or diversified portfolio, sometimes you'll hear that. And what diversified portfolio means is that they're independent of each other. So if one goes down, the other's not likely to go down because of the other one went down. You need that for the central limit theorem because you need an unbiased estimate, which means everything's got to be independent. Okay. So then our mu is 0.09, our sigma's 0.2, but we don't want our mu and sigma. We want now the average of those 20 stocks that we bought. Does that make sense? The average of those 20 stocks, now we can use the central limit theorem. Mu sub x bar is mu, so that's still 9. Sigma sub x bar is sigma over root n. That was the central limit theorem. Any questions on that? Which is 20 over the square root of 30. Sigma is 20, n is 30, and 20 over root 30, I put in my calculator, I got about 3.65. Any questions so far? So notice that our standard deviation went way down. And that's a good thing if you want to get rid of risk. So 3.65 is now our new standard deviation. So let's put that in. And losing money now, remember that was negative forever to zero. And now I hit calculate, and now take a look at the probability of losing money. And what do you notice?
It's very low.
It's very low. So for example, if you're going to invest in your child's account when they're born, then we got many, many years. And if you have it somewhat diversified, doesn't even have to be diversified if it's many, many years, but diversified is a good idea, by the way. There's some other issues. Diversified is a good idea. Then you end up with an average of a 9% interest rate with a very, very low chance of losing. What do you think I did for my daughter's education fund?
You diversified it.
I put it in an index fund. Okay. And by the way, she doesn't have any loans.
So what is the potential of gaining whatever, like
So now if I wanted to gain, if I want to say, what's the probability of gaining, say, what did I say last time? 30%? Zero, basically. Because the standard deviation is so small, you're going to be you're going to be very close to 9%. Do you see that? You might be within 3 or 4% because that's the standard deviation, but you're not going to jump up to 30. So you're not going to, that's why this is not fun money, because you're not going to get to, oh my God, now I'm rich from that $10,000 investment. But you're going to get that solid, very close to 9% each year. Any questions on how this investment works? Any questions? Okay, and this is real. Okay, I've been investing now most of my life, and I've made a lot more than any of my friends, and that's because I use statistics. And I'll show you other statistics as the class goes on that I've used. So you really can make money in this, I promise. You can also lose. It can happen, okay, especially if you're not diversified. Okay, but this is a nice use of the central limit theorem. Okay, I think I made $2,000 today. I don't know if you followed. Now I haven't checked in the last couple hours, but stock market went up a bit. So I've been, again, playing the stock market most of my life now, using statistics. Any questions at all on this example? And this is very much central limit theorem. Okay, so now let's do one more question. Suppose you wanted the standard error to be equal to 0.01. How big a sample size do you need now? Okay, and now we're going to do a little bit of math, and we're going to pop it into the formula. So we want the standard error to be 0.01. So let me go insert, and let me go to equation. So what we know is that our sigma sub x bar, that's the 0.01, is equal to sigma over root n. Any questions on that? That's the formula. Sigma is is 9.
Oh, it's 20, isn't it?
Sorry, sigma's 20. That's what I meant. There we go. Sorry about that. Sigma's 20. And we want to find out what n needs to be. So square root of n. Let me make that bigger so you can see it. So now I got to do a little bit of algebra. Nothing too intense, but I can multiply by root n and divide by 0.01. So let me do those two. And what I can say is the square root of n is equal to, if I multiply by root n, the root n goes to the left. If I divide by 0.01, the 0.01 goes on the bottom. So I'm going to have 20 over 0.01. And that, when you divide by 0.01, that's the same as multiplying by 100. So that's 2,000. Any questions on that? So if root n equals 2,000, what do I have to do?
Square it?
Yeah, square it. Okay. Oh, I think I'm calling sigma 0.20 instead. Otherwise, the number is going to be too big. Let's make that 0.20. It's more interesting anyway. And we're going to say 0.01 as in, instead of 9%, instead of 20%, let's make it 1%. So now I square it, and I get n equals
400.
20 squared. All right, square like that, and 20 squared is 400. So by the way, S&P 500, if it truly is, diversified investment, then that's big enough because that's over 400. Okay. There are issues that it's not really completely diversified. Any questions on coming up with that? Okay, so next is the big central limit theorem for proportions. So here's the central limit theorem for proportions. So remember, proportions are when you have the yes, no question. So if P is a population proportion, the first thing is we use P hat for the sample proportion. I think I mentioned that a couple weeks ago. You don't want to use like we did with X bar and mu, where you did a Greek letter because the Greek letter is too darn confusing. So they use P for the population proportion and P with a hat on it, which is called P hat for the sample proportion, because the Greek for P is pi and everyone gets confused. So we use P hat, and we're going to let Q equal 1 minus P hat. So in other words, if you have, say, a 20% chance of winning, then you have an 80% chance of losing. So Q is the losing, the no's. P is the winning, the yeses. So then the sampling distribution for the sample proportions for sample size n has mu sub p hat equals P, which I already said because I told you that the sample proportion was an unbiased estimator for the population proportion. This is a symbolic way of saying that. And this one's a little messier. Sigma sub p hat is a square root of PQ over n. Any questions on this? Okay, one thing that's very important to note is that n is in the denominator just like before with means. That means that a larger sample size is going to make a smaller standard error. Because if you divide by a bigger number, you get a smaller number. Any questions on that?
Wait, so there's a standard error for proportion as well as for mean?
Absolutely, there it is. There's a standard error for medians, there's a standard error for proportions, there's a standard error for means, there's a standard error for whatever you feel like. But in this class, we're only going to be doing standard error for means and proportions. And also we'll do, in about 3 weeks, difference between two means and difference between two proportions in different ways. But for now, we're just doing means and proportions for this week and the next few weeks. Now comes the next piece, and this is really important. Let me make it bigger because it's where so many people make mistakes. If NP, the predicted number of yes answers, so if you take the proportion of yeses times the sample size. So if you asked 300 people a survey question and 10% of them would say yes, then NP would be 30 because that's how many you would expect to say yes. So that's the predicted number of yes answers. And NQ, which is the predicted number of no answers, by the way, if they are both larger than 5, then the sampling distribution is approximately normal.
No matter the number, no matter the n, the size of n?
NP and NQ have to be bigger than 5. So if n is bigger, then you have a better chance of being bigger than 5, right? Do you see that? So it's n times p and n times q. So n is in there. So it's a combination of n and the proportion of yeses. Okay, so I want you to do me a favor. Put in the chat box the words proportion and the number 5. So put that in the chat box. And by the way, if you're watching this on as a YouTube recorded video, write it on a piece of paper. Do you know why I had you do that?
So we don't forget it.
Yeah, and I'm telling you, more than half the class, and I've been teaching this for a long time, just has 30 in their brain and they never leave it. When you're doing proportions, NP and NQ are greater than 5. Nothing to do with 30, got it? So you always want to think about what is a survey question and how might someone answer the survey question. If they're going to answer with the word yes, then NP and NQ have to be bigger than 5. If they're going to answer with the number 7 or something, then N has to be bigger than 30. So get that down, got it? It's not hard, you just have to pay attention. All right, so now what I want to do, I have a question. And the question is, do the majority of Americans want the government to spend federal money to increase the number of electric vehicle charging stations in the United States? Do you think the majority of all Americans think so?
Yeah.
Yeah.
Okay. You think maybe they do, right? Can you ever find out?
No.
No, you can't. How come?
Population's too big.
Exactly. By the time you finish asking everyone the question, you won't be alive anymore because it'll take you too long. You won't live that long. Okay. And by then, maybe everything will be electric vehicle. Who knows? Like life will be different. So you can't ask everyone. Got
Hey,
it?
so Larry, would this be okay? I know I keep asking you the same question over and over again, but would this be okay to just survey 31 people?
Okay. This is complicated. You're not going to like what I'm about to tell you. You got to wait till next week. Is that all right? So it turns out.
I know it's not that important. I'm just curious because
Yeah.
it's like,
So it turns out if you did 31, you could use a normal distribution. But there's another issue which I got to talk about next week, not this week. Got it?
Yep.
Yeah. And it has to do with, so you can use a normal distribution, you can do the math and all that, because if you used, in fact, even if you did 20, that's probably enough. Even 11 is enough for a normal distribution, because the word, what's the word? Let me ask you, make sure you all know, what's the definition of the word majority? It's an important word in math.
3.5 or over.
Yeah, 0.5 or over, right? More than half of all Americans, okay? Which means basically 0.50000000001 is good enough. Does that make sense? So anything bigger than 0.5. So if you do 0.5 times 11, you're gonna get more than 5. Do you see that? That's 5.5. I purposely don't want to use the word 30 because I don't want you to get into that with means. Nothing to do with 30. 30 is meaningless in this. Okay. It turns out though, if you only used 11, then you don't have good data, even though you can actually do the probabilities, but it won't be very helpful. It won't be inaccurate, it'll just be unhelpful. And that's next week. Trust me.
Thanks.
So I went to Gallup. Okay, and in fact, if you want, here's the article. And the last question that they asked was spending federal money to increase the number of electric vehicles, charging stations in the United States. 59% said yes. Got it? So does that mean the majority of all Americans thinks that?
No.
We don't know.
Right, we don't know because we only know about this. And then, by the way, I'll scroll to the bottom or near the bottom. And we'll see, they only asked 1,017 adults. They didn't ask me, so they don't know. Did they ask you? In my almost 30 years of teaching statistics, I've never had a student saying, Gallup asked me. So almost never happens because we have hundreds of millions of people in America, right? So they can't ask everyone. But here's a bigger question, okay? So we don't know if the majority do. But this is what we want to know. Instead of that, we can say that if it was exactly 50%, which is kind of the highest percent that it isn't a majority, what's the probability that 59% of those 1,017 would say yes? Any questions on looking at it that way?
Say
Can
that
you
one
just
more
repeat
time.
that? Repeat that one more time?
Okay, so if it was 50%, which is the biggest number that isn't the majority, right? If it was 50% of all Americans, so not enough, then what would the probability be if you surveyed 1,017 random Americans that 59% of them would answer yes to the survey question? And if that probability is very, very low, then we can be pretty confident. Does that make sense? If that probability is pretty high, you're going to say, well, maybe we don't have a majority. Do you see? So let's compute. So we're going to use the central limit theorem now. So again, because of that 50%, P is 0.5. 1 minus 0.5 just happens to be 0.5. I'll let you do that with a calculator if you feel like it, but hopefully you know. And N is 1,017, because that was our survey. That was a Gallup's sample size. So now we can say P hat tilde N. We've seen that notation before. So that means the sample proportion has the normal distribution with mean 0.5, because that is right here. Mu sub P hat is always P. We're saying P is 0.5, so mu must be 0.5 also. And then sigma sub P hat is the square root of PQ over N. So our sigma is the square root, sigma sub P hat is the square root, P was 0.5, Q is also 0.5, and N is 1,017. Any questions on how I use the central limit theorem for proportions for this example? Okay, and by the way, this is a recent study. This is, I think, like last month or something. So this is, it's a good study, and Gallup does a good job. Okay, so I put in a calculator, by the way, and I got square root of 0.5 times 0.5 over 1,017 is 0.0157. You can do it yourself, or trust me, you choose. Any questions so far? So what we just have done is we've turned a question about proportions into a question about the normal distribution. And the goal is to see if we can turn everything into the normal distribution, because we just have that normal distribution calculator. It's easy to use. We can do it. Any questions on that? Okay. And by the way, again, if you take 1,017 and multiply it by 0.5, you get over 500. Do you agree? So from the central limit theorem, we need to be bigger than 5. If you're over 500, you're not just kind of close to normal. You are like so close to normal. You could never even tell the difference. Does that make sense? So that's the good news. So now we can actually do the calculation using the normal probability calculator. So we have our mean is 0.5, our standard deviation is 0.0157. We want to find out what is the probability that our P hat will be greater than 0.59, because that's how rare it would be to get 59% or higher. Do you see that? So let's go calculate that. 0.59 will be the low. The high will be a bunch of 9s, because greater than means goes forever. And I calculate it. And what do you notice?
Larger than 1.
not larger than 1. Be very careful. Don't forget to read the very far right of what you're looking at. What does that tell you?
It's very low.
Yeah. And I purposely did this as an example because I want you to get used to this. Happens a lot. What does that E-9 mean?
0, 0, 0,
9
0.
zeros.
Yeah. So it's actually 8 zeros because the first moving the decimal place, you don't get a 0. And the next 8 of them, you get a 0. So it's 8 zeros and then 4 9 or so. So let's write that in. All right. So if we want to,
It was accurate.
what's that?
Does that mean the sample size is fairly representative?
Yeah, the sample size was just fine, like way big. Yeah. The one thing, again, we have to make assumptions is that Gallup did it right, as in they don't have bias. There's probably voluntary response bias, right? And there could be other stuff. My guess, I didn't actually look at it, but if I looked at it now, I'm sure it's gonna be true, is that they use stratified sampling, probably with weighting, because that's what Gallup usually does, and that's what most places do. So they said, they did a random sample. I don't believe that, actually. What that probably means is random dialing of 1,017 adults, 18 or older. As I mentioned, you never ask children. Okay, living in all 50 US states and the District of Columbia. So that's what they said. But, and then they also say each sample of national adults includes a minimum quota of 75% cell phone response. I'm wondering if they're still doing landline and 25% landline response. I have a feeling that they haven't changed their spiel, even though they changed what they do. So I look at this and I say, I don't think so. Do you think they're really getting 25% landline? Most people don't have landlines, so that would be bias right there. Okay, with additional quotas by time zone within region. And then they use random digit dial methods. But there's going to be voluntary response because most people just hang up or don't answer. I got a call today. I didn't answer. Maybe my guess is maybe you did too on your cell phone. Did you? I think I get a call every day that I don't answer. So those are the kind of things that cause bias. So always be aware that there's still going to be some bias. So this is not perfect, and bias, you can't really do much with it other than say it can't be perfect. Any questions on this? Okay. But if this was not biased, then you would say the majority of Americans really think we should spend money to increase the number of EV charging stations. Guess what? We should do that, right? If this is unbiased, we should do that because we're a Democrat society, which means that if majority want it, we should do it. Okay, as long as it doesn't hurt some, specialized minority or something, which it doesn't really. Any questions on this example? Okay, so do you see why the central limit theorem is so important? Every time you do a survey, as long as your sample size is large enough, you can use the central limit theorem, and we will use the central limit theorem. Because otherwise you can never find probabilities because you never know what the distribution is. Okay, so then the last bit, the last example, central limit theorem is for sums. Not quite as important, but it's not nothing. So the central limit theorem for sums. Okay, the sampling distribution for sample sums. So now instead of the mean, we're looking at the total or the sum. For samples of size n has, and then this is something you may not be too used to. What is that symbol? Who knows how to read that symbol that I just highlighted under the mu?
Capital sigma, which means sum.
Yeah, it's capital sigma, which means sum. And if you've had intermediate algebra or higher, then you've seen this. If you haven't, you may not have seen it. And it's confusing because it's still a sigma, but this capital sigma, whereas this guy's lowercase sigma. Sorry about that. I'm not the one that makes notation. I just follow what the statisticians do. And it says that mu sub summation of x is equal to n times mu. Okay, which makes sense because if you're taking the mean of the sums, well, if you ask a whole lot of people and you add them all up instead of taking an average, then you're not dividing by n to take the average. So that's why the times n. That's where it's coming from. And sigma, lowercase sigma, so standard deviation of the sums is the population standard deviation times the square root of n. Very different formula. And the good news is, when it comes to the normal distribution, it's exactly the same as the central limit theorem for means. If the population's distribution is normal, or if the sample size is large, greater than 30, then the sampling distribution for the sum is also normal. So that's exactly the same statement, copy and paste from the first one. Any questions on this big theorem? I'm going to say big, I'm not going to say gigantic. Whereas the central limit theorem for means and proportions, those are gigantic. This one comes up, the others come up all the time. Do you see the difference? Okay, so here's an example, and it's kind of the most common example I usually see, and that has to do with money. Okay, it has to do with business money, not stock market money, but business money. Stock market, you're usually more interested in the means. Okay, suppose that you own a restaurant. If you own a restaurant, it's not the average amount of money that people spend that you care about. What do you care about in terms of money?
How many customers you get?
It's not how many customers either.
How much money, like what your revenue is?
Yeah, what your revenue is, how much total money you get at the end of the day. Isn't that what you care about? What comes into the cash register? Right? That's more important. It's not the average, it's the total. So that when you're talking about money, you're often more interested in sums than you are in averages. Is that clear? For businesses. So suppose the average customer at a restaurant spends $33.23. Okay, I made this up, by the way, but there could be a restaurant with this, right? Okay, and the standard deviation is $9.22 for your restaurant. Okay, if 65 customers eat at the restaurant today, what is the probability the total revenue for the restaurant will be less than $2,000? So kind of what could happen, for example, is, if you own the restaurant, you care about the revenue, but you also care about profit. And maybe you have to pay, your employees and, rent or whatever, and the food costs and all that, that might cost you $2,000. So you might be interested in what's the probability you're going to get, you're going to lose money, because that would suck, right? So that would be an example. Okay, and then also, what is the first quartile for the total revenue for a day? Any questions on the question? All right, so I'm going to literally copy and paste the big central limit theorem, which I wrote as sigma is normally distributed with mean and mu and standard deviation sigma root n. That was our central limit theorem. Okay, and by the way, is our sample size large enough?
Yeah.
Yeah, how do you know?
Over 30.
It's over 30. So we definitely have a large enough sample size. Okay, because if we didn't, by the way, do you know that you have a normal distribution for customer expenses? You probably don't, right? I don't know anything about restaurants, by the way. I've never worked in a restaurant. I don't go to them that often either, but once in a while. But they're probably not normally distributed in terms of what people spend. So the nice thing is you don't need that because we have over 30. So we know it's normal. Our n is 65. Our mu is 33.23. $33.23. Our sigma is $9.22. And our n, again, was 65. Any questions? Any questions on this example so far? All right, so now 65 times 33, if I go to my calculator, I can hit scientific calculator. 65 times 33, 2145. Put that into the mean. We had the standard deviation was this, 9.2 times the square root of 65. So I can go 9.2. And then times the square root of 65. And I get a little more than $74.
The standard deviation.
Yeah. But I wanted an MTP also. That was a standard deviation. And we want to see what's the probability that we're going to make less than 2,000 for revenue. So that means our high is 2,000. Okay. And our low, because we're assuming it's normal, but you can let it be 0. I'll even show you what happens if you let it be 0 instead in this case, but probably should let it be negative 99999. A lot of 9s because 2,000 means you got to have like a whole bunch of 9s because there's 4 digits in 2,000. And calculate. And what do you think? High probability or low probability?
Low.
It's a low probability, around 2.5% chance. Okay, so again, if that means losing money, for example, for the business, for the manager, then it could happen, but it's not very likely. Okay, so notice our probability. Let me write 0.025. So the probability that our sum, I'll just write sum, is less than 2,000 is equal to 0.025. What is the first quartile for total revenue for a day? Well, the good news is I've done all the work already. If I want the first quartile, what do I have to change here?
Probability,
Probability, what should the probability be?
0.25.
0.25. What else do I need to change?
Eliminate the high.
Yeah, I need to make the high blank. Something has to be blank. If you don't make anything blank, it'll let you know, by the way. The low actually is negative 99999. That still works. All the rest still works. And that would be 2,094.97 cents, since this is in money. Okay, or maybe $2,095, because the manager probably doesn't care about pennies.
If you put the low as 0, does it change the high?
Let's try it. So remember 2094.97 cents. Turns out within a penny, it's the same. Sometimes it can change it, but we should know that it doesn't, because the standard deviation is around 74. So 10 standard deviations isn't even the mean. Do you see that?
Okay.
So we don't even get, when you get to 0, that's more than 10 standard deviations away. And 10 standard deviations is meaningless. It never happens, basically. It's not even 30 decimal places, I don't think. So 2095. So we can say the first quartile is 2095. And that would be the first quartile for revenue for that restaurant. Any questions on these examples? One of the things you're going to notice is that we're getting to the point where everything we do is really useful. Okay, I mean, notice that all these things are useful in the real world, and whatever your major is, or whatever you're studying, you can use this. And it gets even more so next week the week after, and continue on. So this class, all of a sudden, you're going to be using it in your life. Okay, I promise. It's one thing I've never had a student saying, what a waste of time, this class isn't used for anything. And you'll get that in the next month or so. I promise. Okay. In fact, there's only one PhD dissertation, one field that you're not going to see statistics in. Any guess?
Philosophy, literature.
No, you can get that. Literature could happen because you can see if how similar authors are, for example.
Art history.
That one you could do also. Should I tell you? You're going to be surprised when I tell you. Should I tell you?
Tell us.
Math.
What?
Yep, math. There's no such thing as having a probability that you're right in math. It's right or wrong. Right?
Do we look down on statisticians?
No, we don't look down on them. Oh, are you kidding? We make a lot of money because we also do statistics because we teach it. But dissertations in math never have any stats in them. But I've read a lot of dissertations from students that got their PhD and they sent me the dissertation to read. It was really cool. And all of them had stats. That includes science, psychology, sociology, all kinds of different subjects. Just let you know, medical, all uses stats. So it's very, very important. But math doesn't use stats. My dissertation had 0 stats in it because it was a proof.
Are we going to start project 2 next week?
Yeah, it's too early for me to even talk about it right now. You should be thinking about project 1 and making sure that's, really good. Okay. And again, some of you sent me your rough draft. So, feel free to, and before I say that, I want to do what I have to do, and that's this. And that is the secret word for the week is sampling, because what this is all about, this chapter, is the sampling distribution. So sampling is the secret word for the week. Okay, and I know some people make the mistake. It's not capitalized. I think that was why some people messed up last week, because they capitalized it and shouldn't have been. So make sure it's just all lowercase, and that's your secret word. Okay, so just a note about projects. I definitely want to read more of your project drafts. And I want to let you know, Braulio, who's here right now, has gone through this a lot and can help you out too, right, Braulio? Maybe you can say something.
Yes, feel free to email me your drafts whenever you have them ready.
Yeah, or if you email me and I give you suggestions, you can email Braulio if you had questions about my suggestions, or did you address them and that kind of stuff. That's kind of thing. He'll help you. So definitely, that can work. And you can go to his Cranium Cafe office hours, and I think they can share desktops, right? Can they, Braulio?
Yes. Yes.
So you can actually share your desktop while he's looking at it too. Okay. And that's very doable. But I want to make sure again that there's still, the secret word quiz, and there's a chapter assignment. But the main thing this week, there's no main exam. The main thing this week is the project. Okay, because that's 10% of your grade. So that you want to, take it seriously. And I'm here to help put in the project discussion board. I'll take a look at it, make sure you're working with your partners. That's important too. So I am done with any new material. Hopefully you are convinced that this is important. And I don't mean just to pass the class, but in life, that this stuff is really used. And it gets even more important the next couple weeks. And I think I'm gonna stop the recording. Well, let me stop the share first, because then it's easier to find. It's more. Stop recording.